Hello, welcome to the makeup lecture for October 15th and October 17th. I'm starting out with our announcements, and obviously you know we're not having class this week in class, and you still can get me by email, Skype, or Yahoo Messenger, so do let me know if you have questions. I did update the death penalty script in that analysis to include functions to do the Cochran-Mantel, Hansel, and Breslow-Day test. And I'll take a peek at that to show you what that looks like. And if you go through the lecture notes section, you'll be able to get to that there. Hopefully the code is annotated enough that you can follow through it. So if you had wanted to get started. The other thing that you need to make sure you do again is download the Breslow-Day code, because you're going to need to source that to be able to use it. Homework 7 problems are posted. I'm going to look at that, and let's go on over there. So homework 7 is up. There is 4 problems for everyone to do, and then, excuse me, 2 problems where you need to choose one or the other. And for the math PhD students, I would strongly encourage you to opt for 511. And that has a different way of thinking through how you might do a goodness of fit test when you've got a continuous measure. So it's kind of an interesting problem. So that's that. And let's take a look. So if you go over to our lecture materials, so a couple things you'll need for Cochran-Mantel, Hansel. So the deathpenalty.r script has been updated. So if you had previously downloaded that, you'll need the new one. This Breslow-Day test script is what you need to source to be able to run that particular function. And let's go ahead and take a look. So the previous version of the script we had gone through, quote, by hand, where I had given the formulas and we had gone through and calculated the statistics, and we had gotten up to this particular point. So all of the code from let's not do it by hand on is new. To automate this, you're going to need to create a 3-dimensional contingency table. And probably the easiest way to do this is to do your marginal tables separate. So if you'll notice, so for our death penalty data, we had 2 different levels of our control variable. So victim's race. So there was white and black. And so what I did, let's look at what our data look like. All right, so there's my data. And the first 2 rows correspond to one of the strata, and the second 2 rows correspond to the next strata. And I am actually taking that. So I'm taking rows 1 and 2, and I'm taking rows 3 and 4, and then I'm specifically interested in, so I want the table, the marginal table, and that information is contained in columns 3 and 4. So that's going to give me partial tables for the 2 strata. So let's run that and look at what they look like. All right, so there's one of them, and there's the second one. And then this right here will create a 3-dimensional array that I'm going to store as a table. And so there's a couple of things in here you'll see going on. To create the array, you tell it what dimensions you have. So the tables are 2 by 2, and that's the x by y dimensions are the first 2 things you're telling it. And then the last piece is telling it what how many strata levels you have. So there's that, and I went ahead and named my dimension names. So that's helpful when you start splitting out a 3-dimensional array. This this unlist will take your matrix and split it all out, and that's just the function needs a whole list of a string of numbers essentially. So that's just breaking it all apart for the function to use. So let's execute that. So if I do that, so you'll see that it gives me, so here's my first strata, it prints out my table. That's correct, so it's good to check and make sure everything's stored right. There's my second strata, and again, I've got 0, 16, 4, so that's all okay. And then, once you've got your 3-dimensional table, so I asked it not to correct. I don't want an exact test. And the mantelhan.test, which is just built in, will run your statistics for you. And so here, so this is actually an uncorrected odds ratio, so that's why it's a little bit different. And below you'll see me doing my adjusted calculations, so that's what we got in class. And unadjusted, let's see. Actually, I'm giving you what we did in class, and then I fixed it for the fact that I had added that number wrong. It didn't make much difference, but I just wanted to clarify that I had that one off. And then here, uncorrected is where it's not adding a half to the 0 cell and all the other cells because of that 0 cell. So that's where that's coming from. All right. So the source statement, so I had set my working directory. This is specifically where that Breslow day function code is stored. So if you haven't stored it in the directory that you're working in, be sure that when you do the source here, you tell it the directory as well. So when I execute that line, it actually reads in that function and it saves it into memory. And now I can just execute the test. And that ran and gives me, again, it gives me my, my common estimate. And then it conducts my Breslow day statistic, and here is my p-value. So this is what matches with what we got in our notes when I went through and talked about the statistic and what it was equal to. All right, so that should get you started in not having to do it by hand. All right, so let's take a look at our lecture notes. So we had just left off at the crab example, and to remind you of what we were doing with the crab data, we were interested in looking at model checking and in particular looking at overall goodness of fit. So the basic idea being that we have expected values, we have observed values, and we want to compare those two. And if our model's done a good job, then our expected values should be close to our observed values. So the other thing that we had gone through is, so the two things that we're comparing. So one, we're comparing a model that contains a separate parameter for each level of your explanatory variable. And we had defined, so the number of parameters that would take would be the number of levels of your explanatory variable. And that would be compared to the model that would be fit using the logit. And with the logit, you would be fitting your alpha, so your intercept, and then plus, so if you would fit x as a linear term, then you just have your intercept and your slope for that, so you'd only have 2 parameters. And our last comment had just been, this is going to work well for categorical explanatory variables, and as long as when you look at your classes, you've got at least 5 in each cell. So for goodness of fit test, you need enough data across your cells for them to work well. And then this was where we had left off. So with the crab data, if you remember, we had looked at width and actually weight as well, but they're highly correlated. So let's suppose you were looking at width and you wanted to fit that into your model, and you were interested in seeing how good of a job that did in fitting your data. Well, one way that you can get at doing a goodness of fit model, okay, so we've done a few that are specific to categorical predictors. It's a little bit more tricky when you have a continuous predictor, so that this would be a good example of looking at how you would go about doing that. And so this takes your variable that you have put in your model, so width, and it breaks it into a number of different classes. And 8 to 10 classes may be a common thing for you to see. And so here we've got 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so they used 8. So deciles are a common thing that people might do. And so for those classes, they go in and they estimate, right? So if you had each of those classes, those would be treated as your response would have a binomial distribution within each class. And so your parameter estimate would just be your sample proportion, because your parameter that you're interested in would actually be the proportion for that binomial. And so this gives you your sample proportion. Okay, so these would be what you've observed. And you also have, so our number of cases we're observing are given here as well. So these are going to be the counts we need for our observed data. And then you need to know what the estimated probability is for falling into that class, and then the predicted number of crabs in that class. So this is going to be your expected count. Getting at this does take a little bit of programming. So if you go to our Blackboard site, I've got a, what did I call that? Let's see. I think I called it like crabgof. Yeah, crabgof.r. So I've already read in my crab data, right? So you've got a number of scripts. The chapter 4 script will get you to that point. And here I am looking at how many unique widths we have. So unique crab width, if I just look at that piece, that prints out all of the unique values that are within the crab width vector. And then when I do length, it just counts up how many there were. So there are 66. Okay, so clearly doing a goodness of fit test at each unique level of width is not going to work. So we're going to need to go through and create some discrete classes. So what I tend to do is use the deciles. The book for this particular one separated it into 8 classes. So I'm just going to show you how to get to their table that they used. And I'm doing this through, so you'll see I've got something I'm calling flags. So this first statement here creates a true-false flag, and it's going to go through and give me true for any crab whose width is less than 23.5. So that's going to be all the crabs that correspond to that first class. So I'm going to do true. And if I do table, and I do has satellite, so that's a 1 or 0, and I do the table only on those that had a true flag, then that's going to count up the number of those crabs in that class that have a satellite or don't, right? So those are the counts that I need for my particular table. So if you'll see, I get 9 and 5. Right, so 5 is, if you look, let's pull up our notes. So 9 plus 5, 14, right? Yeah, 14 cases, and 5 of those had satellites, right? So that's what I'm getting, the 5 and then the 9 not, which means 14 total cases, right? And so I'm literally going through and getting each of those. So the second class looks like that. It's those crabs that have a width greater than 23.25 and less than 24.25. And they're kind of loose here in terms of the equals. So I have equals down here. Technically, it'd probably be better to go through and change this a bit so that you know for sure where the equals is uniquely going to be sitting in the classes. Again, their table doesn't quite make that clear. So true, false, and then I do the table for just those that have that flag being true. And you'll see I get 4 of them had satellites, and 4 plus 10 gives me 14. And I go through and I do the next class. So I've got 17, and the next class had 21. The next class had 15 with satellites. The next one had 20. And the next one had 15. And then the last one were the widest, so over 29.25. And those had 14, right? And 14 had satellites out of 14 total cases. Right, so that gives you those first 2 columns. Number of cases would be the sum of those 2, and then it gives you the number having satellites. Now, to get the expected, I'm doing something somewhat similar. The difference being that you need to sum up the predictions. Right, so let's see what I've got first. So I have flag, so that's going to go back to that first class. So the ones with the least width, so less than 23.25. And my yes, so what does this look like? So the predicted crab is my fit. Right. So that is, you look up, actually that came through from one of our other codes, but that was the model that I had fit. And what I'm doing is I'm taking that fit, which is the probability, and I'm taking the probability for those that have the flag that are falling in this class, and I'm summing them up. So that's the yes, that's the no. This expected, I'm starting out with it empty because what I want to actually do is save them, right? So that just, there I just printed it out. So the number of yes is 3.63 and everything else is remaining as no. And this expected here, so I am appending them to each other. So I started out with nothing unexpected, and if you look, if I print it, I just stuck on what I just counted. So flag for the next class, sum up the probabilities, take the total minus the number of yeses, so that'll give you the ones that don't have a satellite. And then I printed it, and then I saved it. So here's the printing it, and here is the saving it. And if I type expected, you'll see that I've got, this is the yes and no for the first class, this is the yes and no for the second class. And then you keep going. So I'm doing that for each and every single class. There you go. And my observed, so my observed I actually ended up typing, I didn't feel like pulling it all out from above. So these are the observed counts. And my expected, right, so let's look at how I wrote that out. So observed, so these are the number of yeses, the number of no's. Expected, so this is what I just got, my number of yeses, my number of no's. And then I'm going to do a chi-square. So observed minus expected squared divided by expected. And there is my statistic. And the difference, so if we go back over to our notes, right, so the degrees of freedom, right, so I had 8 classes, so I'd have 8, and the degrees of freedom for my reduced model, I just have my intercept and my slope. So the degrees of freedom here then are 6, so I have 6 degrees of freedom. And my chi-square, which is what I'm fitting here, equals a 5.3. And that comes directly from here. So there's my goodness of fit by a chi-square. And the p-value comes out to be quite large, so 0.5. The likelihood ratio test, so you can do the likelihood ratio test, not with the simplified form in the text because there is a 0 cell in there, but you can go back to the likelihood and compute the likelihood ratios test. And if you do, you'll get a value of 6.2, a p-value of 0.4. And so what do you conclude from this? Right, so your reduced model, so your null, let's pull something up so we can write on this. Right, so first of all, your degrees of freedom was 8 minus 6, 8 minus 2, sorry. All right, so if you think about what your null is your reduced model, right? So your more restrictive model. And here, this is actually your logistic regression. It has 2 parameters. Whereas your alternative is the saturated model, which had 8 parameters. Okay, so it provides a complete fit to your model. So if we think about what our p-value was, so our p-value is large, relatively, probably by anyone's standards, 0.5 and 0.4. So we would not reject our null. All right, so let's look at that again. So we are going to fail to reject our null hypothesis. And this means that there is no evidence for a significant lack of fit. Right. So the model that we fit performed fine. So the logistic regression did a good job of fitting the observed data. All right. There you go. So that would be a goodness of fit test. You only have to go through and construct those individual classes if you have a continuous variable. If you naturally have a discrete variable, you automatically have the fitted values. You automatically have your observed counts, and you just use them as is. So that's just an example of what to do otherwise. It certainly gets a lot more complicated if you've got lots of explanatory variables. You can do it. It's going to take a good bit of work, but just something to be aware of. Residuals. So residuals would be another way of getting at this. So maybe you don't feel like going through and taking multiple discrete variables and constructing some kind of a goodness of fit test that combines over all of them. An alternative would be to look at your residuals. So that would give you an idea of where you might have some lack of fit. And we had previously defined the Pearson residual. So the Pearson residual has your variance in the bottom. But your variance in the bottom is not taking into account the fact that we actually are using an estimated quantity for the mean in the top. So its variance is going to be a little bit too small. So while its large sample will look like a normal distribution, the variability is not going to be appropriate, right? You can use it as somewhat of a gauge if you have a reasonable enough sample size. You could use the 2 as kind of a 95% guide to look for lack of fit, just kind of as a heuristic. But preferably, you go through and you use the hat values and construct the standardized residuals. And we can do that easily in R, and we've had the programs to do that already. Another measure, one that we have not used before, is something called DF beta. Right? So this gets more to individual observations. So the idea being, if you have an observation that if you were to remove it, your parameter values would change quite a bit, then that would be a particularly influential observation. Right? It might not be an outlier, right? So you need to look a little bit further and see, okay, why does that have such an influence? But it at least helps you identify points that might alter your conclusions, and that way you can give some thought to whether you believe those are reliable samples. And there are a couple of other measures that are detailed in the book. The DF beta is a reasonable one to use, and we'll look at how to code this up as well. So for each parameter in your model, this gets you the change in your parameter estimate if an observation is deleted. So if you think about that, for each parameter and for each observation, you're going to have a value for this. And then you're looking for, is there a particular observation that seems to affect, maybe it's only one parameter, maybe it's a number of parameters, but that's the kind of pattern that you're looking for. And there is a DF beta function in R that we can use to compute these. So let's go through a more extensive example. And this is data on admissions. So we're looking at a number of different departments, so 6 departments, admissions data to Berkeley. We've got students classified on whether they were male or female, and then whether they were admitted or not. Okay, and so if you think about, so what would your response be? probably you would assume that it's admission status. We're interested in predicting admission status. The variable that we're interested in comparing to that, your explanatory variable, would be sex, so male or female. And a variable that might alter that relationship would be department. So this would be your control variable or potential confounder. So our Z variable is going to be department. All right, so we're going to go through the whole process. We're going to use all of our tools to step through this. So before I start into this, there were a couple of typos in the R code, and so I've updated the notes from here to the end. So it's a couple of places it'd probably be worth you reprinting the corrected notes, and I'll point to where that's at. The R script has also been updated, and I just did that tonight. So if you have downloaded it prior to, and it is October 17th, you'll need to get the new version. So let's see what we've got. So this is the admissions data, and I've set my working directory, read it in, and I created a dummy variable to indicate that I've got female sex. So here I've got indicator of female, and then I printed out my data set to have a look at. So here is the data set. I've got number total, so this is not individual level data, so I'm going to use these totals to specify that I have weights when I do my GLMs. So it's just to make sure that you remember to do that, otherwise you'll have a very different model. It'll think you only have 12 observations. And then I'm going to be interested in modeling the probability of admission. So that estimate would be the number of yes over the number of total. I will use that as well. Effects that will be important would be to look at sex and to look at department. So I'm going to look at each of those separately to get a feel for whether they're significant as a main effect. And then I'm going to look at them together. So let's see what we've got. So the first model I fit is, I've got binomials, I've got a logistic regression in my GLM. Here's my weights, so n total, so it tells it that I've got tabulated data. And I am just fitting the female indicator variable. And so if you go down, you'll see that alone, there is a significant difference when it comes to looking at admissions between the two sexes. Right? Department, so another thing to be careful of, my departments were numbered 1, 2, 3, 4, 5, 6. Those numbers aren't meaningful in any way, that's just a label. So you need to either treat it as a factor, which is what I chose to do, or create dummy variables. So here I am asking R to treat that as a categorical variable and create those factor levels for me. And so this model, model 2, will look at whether there is an effect of department on whether or not a student is admitted. And if you page over, you'll see that there is a highly significant effect of department on admissions. Right? So each of the effects seem to be important for admissions. So if we put both of them in the model, oops, and that is right here. So I've got female and my factor variable for department, and have a look. Something interesting happens. So you see that the effect of sex actually drops out. So the p-value for that is now 0.217, so clearly not significant. But admissions rates do depend on department, right? So at this point, you might want to start looking at, well, does this model provide a good fit? Is there something else going on? And so one way to do that would be residuals. Another way to do that would be the goodness of fit test. So the first thing I've got here is my standardized residuals. You'll see I've got my Pearson, and then I've corrected it with the square root of the 1 minus the hat hat value here. And I printed it alongside the department and the sex information so I can get an understanding of if I have large residuals, where are they, who are they large for. So I've got 12 different observations, and I would not expect many of those to be extreme, right? So these, if the model is fitting well, should follow a standard normal distribution. And 95% of the time, you expect them to fall within 1.96 to minus 1.96, right? So the fact that we've got a couple of these that are 4 is very surprising. So that indicates that you've got evidence that there's lack of fit, and particularly Department 1 is not being fit well by this particular model. So for my goodness of fit test, and this is where the new handouts have a difference, so I had a typo here. And in particular, I forgot to include my no variables. So, what we've got here is the expected yes. So I've taken my fitted values, which are my estimated proportions. That would be times the total, so that would get me the expected number of yeses that my model gives me. The expected number of no's then would be total minus expected yes, and then I'm sticking those together into one. Observed would be just the number of yeses and the number of no's. And then for my chi-square goodness of fit, there's my statistic, observed minus expected squared divided by expected, and then summed all up. On degrees of freedom, so the different levels I've got in my explanatory variables, I've got 6 levels for department and male and female. So I've got 12 different levels in there. And my model, so if it helps to look back, I've got an intercept, I've got a model fit for our sex, and I needed 5 dummy variables for department. So that gives me 7 parameters in my reduced model. So degrees of freedom are 12 minus 7, which is 5. And that gives me, so my chi-square is around 19, and the p-value would be the probability of having that or larger with a chi-square of 5 degrees of freedom. And that's pretty significant. So it comes out with a p-value of 0.002. And so that tells you that you do have a lack of fit. And if you combine that with the information from your residuals, that tells you that it seems to be coming from Department 1. So you might consider leaving Department 1 out and see what the rest of your data might be telling you. And so that is what we are going to do next. All right, so model 4 looks the same with the exception of this piece right here. So it's got a subset command in it. And this is a nice little tool I actually just recently learned. And so this allows you to subset your data, and your model is fit only on the data that fits that particular criteria. And so if you look at what I put in, I'm saying department not equal, so that's the exclamation point and equal sign. So department not equal to 1. So that's going to take all departments except for 1 and fit the model on them. So when I do that, so here's my model 4, and I'm summarizing it. So sex is very much not significant. My p-value is 0.724. Departments are significant. Oops, flipped a little fast. So you'll see Department 3, 4, 5, and 6, very significant. When I look at my residuals, so here I did standardized residuals for that model leaving out Department 1. Notice they all look very, very nice and small. My goodness of fit test, and again, here I corrected it. I now have my nose in there. A little bit of finagling because you need to make sure you've got the departments that don't include 1. So that's what this index is doing for me. So I pulled out my yeses and my nos for my expected model to compare with my observed model. Let's see, and I end up with consistent with my residuals. I have no evidence for lack of fit. So a model fits, and department 1 really was the one that was throwing off my model. DF beta, so you might want to see, are there any particular observations that could be throwing this model off, right? So if this is a model that you're ready to believe in and you think you've got a good fit, DF betas would be one additional check. And going through, so what you're looking for are large values, right? So if I look, this is telling me that my intercept, when I leave out observation 8, is changing by a -3, right? Department 3 is changing by a 2. Okay, so yeah, it might cause you to look back at observation 8 a bit. However, observation 8 is actually the one that's serving as the reference group. So that's kind of a, look for effects that cause large shifts in your coefficients. But observation 8 happens to be the one that, if you took it out, your reference group is going to change. So of course, you're going to get shifts in your parameters. So that's not too surprising. Let's see. So female was not significant as a predictor variable, so you should drop it. So the next model I did was I kept with my subsetting, so I threw out department 1, and I just fit the factor for department. And go through. Again, so I'm looking at this. Department is a significant predictor of admissions. I looked at my residuals. My residuals are all small. I looked at my goodness of fit test. All good. I looked at DF betas. You run into the same issue if you throw out the particular variable that's defining your baseline. Well, of course, you're going to have large changes, but that's just a model definition effect. So let's see. So in terms of some summary, so I would go through and for your model, so I've got my E to my different coefficients. So this gives you the admissions, your odds of admissions for department 3 compared to department 2. Same for 4, so odds of department admission in department 4 compared to 2, 5 compared to 2, and 6 compared to 2. And we're not given here what those departments are, but our relative comparisons are all to department 2. So we left out department 1, so you should summarize that separately, because at least for departments 2, 3, 4, 5, and 6, there's no difference in admission rates between the two sexes. But there was something different going on in department 1. Right, so separate, what you would want to do is go through, and so this is the table that shows you the admissions data for department 1. And here I went through, I fit the model just for department 1 to see for that particular department is sex significant, and it is. So that particular department has something going on that has differential admission rates for females compared to males. Notice that I did that by saying subset only to the department equal to 1. So that's the only thing that's going to fit. You'll see that the sex effect is very much significant. And in particular, so at the bottom I've got E to my coefficient, which is 2.86. So that tells me the odds of admission for a female student are 2.86 times that of admission for a male student. So females are being preferentially admitted in this particular department. And then you can also add on your likelihood ratio confidence interval as well. So that would be 1.75 to 4.9. So it would be some additional interpretation. So getting to conclusions. So I would step through and note that due to Department 1 having a difference in its particular pattern with respect to sex, and you could give some of those statistics that we've gone through, it was considered separately, and conclude also by providing summary values for what the admission rates look like for the other departments and information on the fact that sex was not significant. You could provide the model with that and with the p-value for sex, showing that it was not a significant effect for those other departments. And that would wrap it up. You could give a goodness of fit test for your final models just to establish that you fit your data well, and then that would do it. So that will bring us up through the notes that you have, and then on Monday when I am back, I think that's the 22nd, we will start into multi-category logit models. So I will see you then.